Hi, my name is Igor. I am an undergraduate student of Mechatronics Engineering at UFSC Joinville and a member of the Vehicle Refrigeration Laboratory. In this video, I will present the work entitled Transient Thermal Load Evaluation of Refrigerated Cargo Compartments. The transport of refrigerated cargo plays a fundamental role in the supply of perishable food, allowing the maintenance of these products in good condition and safe for consumption until their arrival at their destination. In 2019, Brazilian exports of chilled and frozen bovine meat was responsible for a turnover of $6.5 billion, equivalent to 3% of the national exports. Through these informations, we can note the great demand and the importance of transporting perishable cargo to the country. Some papers address important topics related to the refrigerated cargo transport. Tissot et al. Evaluated the effects of heat and mass transfer on the energy consumption of refrigerated trucks. The authors found that the use of air curtains can generate energy savings up to 40%. Da Silva e Taglialenha developed a steady-state mathematical model to evaluate the energy consumption required to transport refrigerated products, considering geometric and operation parameters. Looking et al. Developed a strategy to control the internal temperature of refrigerated cargo compartment in relation to external thermal disturbances. Artuso et al. Proposed a dynamic modeling of a truck's refrigerated cargo compartment during operation and evaluation of the peak refrigeration demand. This work has the following objectives: implement a mathematical model capable of predicting the transient thermal load of a refrigerated cargo compartment, and evaluation how the physical and constructive parameters of the cargo compartment affect the refrigeration system performance and the internal compartment temperature. A schematic of the studied system is shown in this image. In it, we have a truck equipped with a cargo compartment and a cooling system. The compartment interacts with two external heat sources defined as the thermal load due to the solar irradiation, Ks-rad, and the ambient thermal load, Ks-amp. While part of these parcels is accumulated on the compartment walls, the rest is infiltrated in its interior, this being Ki. In order to keep the internal temperature Ti within acceptable values, the infiltrate load must be removed by the refrigeration system, whose capacity is represented by Ki refrig. The system was modeled based on the first law of thermodynamics and the fundamentals of heat transfer. Energy balances were applied on each face of the refrigerated compartment and in its interior. The solar position was considered, which continuously changed the thermal load Ks-rad along the path of the vehicle. The two main equations of the model are the following. The first represents the derivative of the internal temperature related to the time, that is equal to the infiltrated thermal load minus the cooling capacity, Ki refrig, divided by the sum of thermal capacities of the internal air and the products inside the compartment. The second equation is related to the derivative of the surface temperatures relative to the time, that is equal to the Ks-rad, that is the thermal load due to the solar irradiation, plus Ks-amp, that is the ambient thermal load, minus the infiltrated thermal load, Ki, divided by MSCS, that is the thermal capacity of each surface element. Additional equations were used to evaluate this derivative. The system of equations was numerically solved in a computational algorithm whose flowchart is shown in the right side in this image here. The physical and constructive parameters investigated in this study were the following. In the table on the left, we can see the external dimensions of the compartment, and in the table on the right, we can see the considered insulation thicknesses cases in this study. We have used 4 insulation thicknesses for this study with the values of 50, 80, 100 and 120 millimeters. The first result obtained was this graph. It shows the internal temperature of the compartment throughout the day for the different insulation thicknesses studied, with the cooling system deactivated. We can see in this graph the time of day in hours in the horizontal axis, and in the vertical axis we can see the temperature in degrees Celsius. We can observe peak values of temperature of approximately 57 degrees at 10 a.m. and 3 p.m. due to the maximum of irradiation in the surface at these times. Another result obtained was this graph. In it we can see in the horizontal axis the time of day in hours, and in the vertical axis we can see the cooling capacity in watts. This graph compares the transient cooling capacity for different insulation thicknesses of 50, 80, 100 and 120 millimeters. We can see peaks of cooling capacity also at 10 a.m. and 3 p.m. of approximately 2200 watts for the case of 120 millimeters and of approximately 3900 watts for the case of 50 millimeters, a difference of 45% between these two cases. In this figure we can see a bar graph with the internal temperatures at the time of the peak thermal load in the system, 10 hours, for each of the studied insulation thicknesses. We can see in this graph in the horizontal axis the insulation thicknesses in millimeters, and in the vertical axis is the temperature in degrees Celsius. We can observe in this graph that the minimal temperature is related to the insulation thicknesses, with the greater insulation thicknesses reaching smaller internal temperatures. In this figure, we can observe the influence of painting absorptivity on the compartment faces in its internal temperature for the cases of 50 and 120 mm insulation thicknesses. We can see in the horizontal axis the time of day in hours, and in the vertical axis we can see the temperature in degrees Celsius. It's possible to note that the increase of absorptivity leads to elevations in the internal temperature for both cases. For the case of 50 mm, we can see an increase in the internal temperature from minus 26.5 degrees Celsius to minus 25 degrees Celsius. For the case of 120 mm, we can see an increase from minus 38.5 degrees Celsius to minus 36 degrees. This figure shows the influence of painting absorptivity on the compartment faces in the system power consumption for the case of 50 mm insulation thicknesses. It can be seen that the elevation of absorptivity causes an increase in the system power consumption. We can observe in this graph that in the horizontal axis we have the time of day in hours, and in the vertical axis is represented the power consumption in watts. As can be seen for the insulation thicknesses of 50 mm, the painting absorptivity change from 0.3 to 0.98 results in an increase in the maximum values of power consumption from 3000 watts to 3250 watts. This represents an increase of 8% on the power consumption. Here in this slide we can see two tables. The first table shows the fuel consumption for the cases of insulation thicknesses of 100 and 120 millimeters. In this case, it's noticed that the increase of the thermal insulation thicknesses from 100 to 120 millimeters reduces the fuel consumption in 45%. The second table shows the fuel consumption for the values of absorptivity of 0.3 and 0.98 and the insulation thicknesses of 50 millimeters. As can be seen, the change of the painting absorptivity from 0.3 to 0.98 results in an increase of 1 liter of diesel. That represents a difference of 8% for this case. It can be seen that both the parameters affect the system fuel consumption. However, it's also noticed that the insulation thicknesses has a larger effect than the absorptivity on the fuel consumption. We have the following conclusions for this work. The infiltrated thermal load and the cooling capacity were evaluated, showing difference up to 45% between the cases of 50 and 120 mm of insulation thicknesses. Peaks of thermal load were identified at 10 am and 3 pm in the simulations, due to the maximum of solar irradiation thermal load at these times. The results also show a reduction in the infiltrated thermal load amplitude related to the insulation thicknesses increase. It was observed that the insulation thicknesses affects the minimal internal temperature reached by the refrigeration system. The results shows that the minimal internal temperature can be reduced by 12 degrees Celsius by increasing the insulation thicknesses from 50 mm to 120 mm. It was verified that the insulation thicknesses has a larger effect than the painting absorptivity on the system fuel consumption. I would like to thank you for your attention and interest in the work. I would also like to thank the Scientific Initiation Scholarship Program, PBIC, UFSC, the Vehicle Refrigeration Laboratory, HEVI, and Professor Diogo Lôndero, the other author of this work, who helped me greatly during the development of this project. Thank you.